My name is Jason Gerald. I'm very fortunate to be leading an amazing team at NextGen Interactions, and today I'll be presenting our work, a customized input device for simulating the detection of hazardous materials. Essentially, this talk is about how we built a SteamVR compatible input device specifically for firefighters' needs. Some background on the project. The larger picture is this is a subset of a FirstSim VR project funded by the National Institute of Standards and Technology, Public Safety Communications Research Division, specifically with their enhanced user interface user experience group that is also very experienced with augmented and virtual reality technologies. And so some of the problems we're looking at are that experimental tools, by definition, they're not ready to be used or fully tested. Most importantly, out in the field. They're in the lab, and so it's difficult to evaluate and optimize those in the context that they'd actually be used. Another challenge is that today's best hardware, I think most people would agree, is the consumer level gaming entertainment systems. But those are great systems. They convey amazing experiences, but they're not built for public safety. In addition, current simulations, I think everyone here at the conference is pretty well aware that simulating this sense of touch is a pretty challenging task. And so we're taking on some of these challenges. Our high-level goals are to develop and prototype first responder tools using mixed reality, and also researching the effectiveness and the transferability of those mixed reality simulations. We've been working pretty closely with firefighters. In fact, we've hired 3 firefighters part-time, not only to advise us, but in order to provide us direct access to the larger firefighter community. And that's resulted in a lot of one-on-one discussions, some focus groups, and providing feedback formally and informally through questionnaires and such of our early work, such as our demos, but also just questionnaires of what use cases do they think might be relevant for these mixed reality simulations. And it turns out the need we really weren't aware of, and so we would have never came up with this device ourselves. Talking to different firefighters, there were a lot of challenges for training to use these sorts of devices, these gas monitor, air monitor type devices. And hazmat training of using these devices is typically done in a lecture format. It describes the theory, there's math involved, etc. But in a stressful situation or not being able to have the readings on the device update in real time can be a big challenge. There's not a good way to have those actual readings update unless there's a dangerous gas actually in the environment. And so what's done is a lot of discussion of the trainer, essentially drawing attention to the air monitor and saying, for example, your LEL level is at some number, essentially giving away the answer when the user might actually be more distracted in the real world incident. And so that experience is, crucial to using these devices, but that experience is only gained from those rare and dangerous real-world incidents, those low-frequency, high-risk sort of situations that can take quite a while to build up that experience. Now, these air monitors, even though they are quite expensive, they're available on a lot of fire trucks. But your typical firefighter does not use them because they're not confident in using them, because the only way they gain that experience is by using them in those rare, dangerous situations. And so they often call in the hazardous material specialist, and that can result in a lot of delays. And when there's dangerous gases out there in someone's home or in industrial settings, delays can be very bad. So here's some early sketches once we learned that this might be a good use case of our designing the physical device. You can see on the upper left there is a very early sketch of a simple device and where the SteamVR compatible sensors might go, a more refined sketch, and then a model that has different places to place the sensors. You don't actually, each of those indentations is where a Steam VR compatible sensor can go. You don't actually need that many sensors, but this allowed us to try putting sensors in different places without having to necessarily completely reprint the prop. We can also take a look at that in software. This is done with, this is a screenshot taken from OpenSCAD of where those sensors might be placed. And then here's a more refined model of what the thing would look like. And then the actual 3D printed props with electronics provided by Virtual Builds. And basically wire those up and do a lot of experimentation. It does take a lot of iteration on these things to kind of figure out what works well and you know, how to place the sensors in different configurations and such. But like anything, the more experience you get with building these sort of things, then the better you get at it. And here's our most recent version of the device. You can see it's got some covering on there. Those are infrared transparent that the lighthouses can see through. And to be able to cover the sensors, one of the sensors is on the bottom there, not covered. And you also notice that the rubber grip there is actually what we purchased to cover the normal gas monitoring device. So we designed and printed this to be the same size of the device so that the covering could go over that so it feels more like a real device. Now also notice that it's also got some holes in that. The device actually had that, so we were able to design the placement of the sensors to match the real covering, and so we didn't have to modify that covering. The actual experience here is on the upper left corner, a user holding the device in his hand, and on the bottom left you can see that what he's seeing virtually. And so you can see there's different readings and such on that device, and here he's doing what's called a bump test. That's essentially to check the calibration on the device before you go into the dangerous situation to make sure your sensors and such are reading properly. And here's a more enhanced implementation where we have an instructor explaining the device, how to turn it on and perform that bump test. And here the user is actually taking it out to the hot zone, to that dangerous situation where they can practice using the device in that dangerous situation. And here is a video of the experience. You can see we're using leap motion here for hand tracking. We had to use that. We couldn't use controllers because they need to actually pick up the device. And the user here starts off by skipping the narrative so they can go straight to the interaction.
Okay,
and so the instructor will guide the user through using the basics of the device to start with.
Go ahead and grab your air monitor. Turn it on by pressing the red power button on the right.
You can see the physical pelican case matches the virtual to provide that additional sense of physical touch there, as well as the device feeling more
like
that actual
up,
device.
Four sensors on the screen. As I'm sure you know, those are oxygen, LEL, CO, and H2S. Go ahead and do a quick bump test by putting the meter up to the test cup attached to that cylinder. It's filled with the calibration gas for all 4 of our sensors. Looks good? Then let's head out to the hot zone. Okay, looks like our ride is here. Jump on the back and let's head out.
Okay, so the user proceeds to ride out to the scene of the incident and continues using the device, and the numbers change based on where he's holding it, how long he's holding it, etc. Okay, so as far as future work goes, we are designing user studies now and conducting pilots in order to evaluate how useful and does this better match real-world performance? Our research question being, does adding these sense of passive haptics, in this case the physical device in your hand versus a controller, does that result in better matching to real-world tasks? And so the hypothesis is adding passive haptics to a VR experience results in task performance that more closely matches the real world. The specific measure that we're starting with is very simple, time to completion, and we're comparing those time to completions for 3 conditions. That is the real world. We've built a real world case that matches the implementation of the VR case. So that essentially we're not putting them in the dangerous situation for the user study. We have created a simple office environment virtually that matches our physical office environment. So we're trying to match those different things up to minimize confounding factors. And then on the VR side, we've implemented just a standard VR implementation, then a VR implementation similar to that, but instead uses passive haptics. And we're trying to see if the performance of the VR with passive haptics more closely matches the real world performance. And I want to emphasize here that better performance, that is shorter time to completion, isn't necessarily better. We're trying to understand if what factors can better match real world performance, even if that real world performance is slower. And so, for example, holding the multi-ray, you have to hold it up for a certain amount of time. You don't want to just go through the task quickly. Another sort of analogy of that is if you can teleport and move pretty quickly in virtual reality, but that does not necessarily mean that it matches the real world better. We're trying to look at this to see if that transfer, if the simulation results will transfer to the real world so that we can train them in the same way that they would learn in the real world and apply that to the eventually those dangerous situations. We believe this work, and continuing on this work, will eventually lead to improved evaluation of not just the interfaces and the tools, but the actual processes that are wrapped around those tools. So we can refine those processes and improve the use of those processes for firefighters out in the field, because we can kind of try different things in a safe environment, even though it may not it feels safe as in the lab. It at least somewhat matches those dangerous situations first responders find themselves in. And so that will result in ultimately increased safety by providing those better designed tools, because we can iterate more quickly and more efficiently and better. As well as decreasing cognitive load through these new tools by not necessarily having to look at the device. We can start looking at the physicality of those devices, and so that you can feel the interface, especially super important for first responders. They don't want their situational awareness taken away. If they're looking at something dangerous, it'd be nice to be able to sort of feel their way through the interface without having to look at it. We believe this work will also lead to better training transfer. That's sort of the purpose of the user studies, in order to evaluate if it better matches real world performance than just the straightforward implementation without the sense of passive haptics. And most importantly, leading to faster response to these critical incidents. If you have these dangerous gases out in the world, delays can lead to significant problems. And so ultimately these tools, we hope, will lead to these faster responses and a safer world. Okay, with that, I'd love to take a couple questions. Thank you for your time.